All right, so I think we should be going live now. Awesome. All right. It's been a while since I did a LinkedIn live stream, so let's see how this goes. Either way, we're still recording. Hopefully y'all can see me. We're about to get started here in just a second. Can't see my live stream for whatever reason, so I'm just gonna trust that it is going the way it's supposed to. All right, y'all. I'm thrilled to have with me here Rohit Jena, one of the authors of an intriguing paper titled Hedging the MAP, Post-Processing by Multiple Solution Proposal and Selection. Rohit and his team tackle a fascinating issue in modern instance segmentation networks in this paper. As many of you might know, these networks are often evaluated using a mean average precision or MAP metric. However, the team identified a significant problem. These networks tend to produce many low confidence predictions, a phenomenon they refer to as hedging. Hedging comes in two forms. There's spatial hedging, where predictions are spatially perturbed versions of each other. Then there's category hedging, where the model hedges on the category of the object with a single mask. While these hedged predictions can slightly boost the map, they can often lead to undesirable user results. Rohit and his team propose a new method, semantic sorting and non-maximum suppression, to address this. This module is designed to mitigate the problem of hedging without sacrificing the quality of masks produced by the network. They also propose new measures to quantify the extent of hedging in a network's predictions. Rohit, thank you so much for being here, man.
Yeah, thank you for having me. Yeah, it's pretty nice being here.
Yeah, and it's nice to get a chance to record not on the floor of CVPR and somewhere nice. So, I kind of like to, and not everybody in my audience is a deep learning practitioner experienced. Most of them are like me, maybe just a year and a half of experience of deep learning. So I kind of always like to start with some like background knowledge questions to get the motivation of the conversation kind of in place. So let's start real quick by talking about instance segmentation. So what is instance segmentation and why is it important in deep learning?
So segmentation broadly basically refers to extracting out objects in the image. So like you take an image from your phone or whatever, it is in the space of pixels. You just have a bunch of pixels. There is no meaning like as to what those pixels mean, right? But segmentation basically refers to extracting the objects out. So if you take a picture maybe of this table, you see there's a cup, there's like a pot, there's like a milk carton or whatever, these are objects, and extracting these objects is the problem of segmentation. You could either just try to extract the classes. So for example, if you have cups, I could say that this region is the cup region. That is semantic segmentation. You just assign semantics to each pixel. Or you could say this is cup 1, this is cup 2. This is instance segmentation. You are also telling instance apart from each other for a given category. So this is what instance segmentation is broadly.
Okay, cool. And there's a metric that's commonly used in instance segmentation. This is called mean average precision.
Right.
I guess if you could briefly describe what mean average precision is, and then also kind of what are the strengths and limitations of mean average precision, and why is this the go-to metric despite its potential shortcomings?
So mean average precision is basically, I think an easy way to explain this is you have a bunch of predictions. You have a bunch of ground truths, like what objects are in the scene. You try to match them up based on the confidence of your predictor. So your let's say my prediction is like, this is a coffee cup, this is a coffee cup, this may be a coffee cup, right? And so I have 3 predictions, but there are 2 coffee cups. So I have like, 2 true positives, and then this is like a false positive because I predicted something that isn't there. So the MAP in this case would be somewhere around like 0.6. So think of it as like a weighted precision recall average kind of, like the details are more involved. I think it's basically the area of the, so if you try to plot a precision versus recall curve, you would see something like this, where the precision goes down, recall goes up. You try to predict more and more, and the area under this curve is the MAP. And it has been used for around 10 years now, I think. So first, I think it came out with the COCO challenge or VAOC Pascal challenges, which was like really back in the day, I guess. I mean, 10 years is a long time frame in this day and age, but yeah.
Well, so 10 years ago, do we have like tasks like instant segmentation, semantic segmentation, or is this kind of approach to segmenting an image also?
I think we had segmentation like even before 2000. I think the lack of benchmarks and the lack of an evaluation protocol was not there back then. And I think this, like, basically the COCO benchmark, and like, once you have a huge curated data, the last year, but I think the last 10 years, but like the problem was always there.
Yeah. If let me just make sure my internet connection is good. Object detection really as well. It's this concept of non-maximum suppression. So if you can kind of describe what non-maximum suppression is for instant segmentation, and maybe give us a little bit of intuition into how this affects the model's predictions.
Right. So before I maybe start, let's look at a problem of classification, right? So let's say you have a dog versus cat classifier, and for each image you only have one prediction, whether it's a dog or a cat, right? So in instant segmentation, the problem is you do not know how many objects are there in the scene, right? So there may be 2 coffee cups, there may be 4, there may be 20. You do not know a priori, right? So what you do generally is you assume there's coffee cups everywhere in the scene, right? And at each location in the image, you're coarsely at each location in the image, you try to say, is there a coffee cup here? Is there a coffee cup here? Whatever, And once you aggregate all the results, what you will have is, for example, if you look at this and this pixel in the image, you will discover the same coffee cup twice, right? So what non-maximal suppression does is it will keep one of them and discard all the others, right? And this is done because in instant segmentation, you do not know how many objects there are. So you tend to over predict in the beginning. You try to predict as many as possible, and then you see which ones are like just duplicates, and you remove those.
And so I'm assuming that leads to a lot of false positives.
Yes. So in the beginning, like initial architectures sort of like try to mitigate this problem. So you over predict, and then an NMS will basically clean up everything. But what happened over the years is more modern architectures came along, and they proposed not using NMS, or rather using like softer versions of the NMS, which do not explicitly discard the duplicates, but rather just lower their confidence. So if I have 2 coffee cups that are like high confidence, I'll lower one of their confidence to like 2%. And so this basically leads to the hedging problem, because now you do not know where to threshold, and if you threshold your MAP, sort of false.
Okay. Before we dig a little bit deeper into hedging, let's double click on false positives. Sure. So talk a little bit about what false positives are for image segmentation and why they might be problematic.
Right.
But how does the balance between false positives and false negatives, like how does this shape the design and evaluation of a model?
Right. So different applications will need different types of, like you will prioritize different types of metrics. So for example, in a medical setup, let's say you're trying to do tumor prediction or tumor segmentation, right? False positives are fine, because even if you segment something that's like a tumor, but it isn't actually, it's okay. The radiologist will look at it, be like, oh, this is not a tumor, it's a false positive. False negatives are catastrophic. If you were not able to predict a tumor and that grows in 5 years, and now you have cancer, that's life threatening. In some cases, you do not want a lot of false positives, maybe, where like if you only care about precision, then it's okay to miss 1 or 2 objects. Let's say you're doing some kind of tracking, right? So maybe you want to keep, maybe you do not care about segmenting all the objects in the scene, but just the one that you have should be like, you should be able to track it, for example. And that's where you maybe do not want a lot of clutter, right? You're trying to capture 1 person and you see like 5, which one do you track? Right?
Yeah.
That's where false positives might be harmful.
So talk to us about this concept of hedging.
Mhm.
So what does it mean, particularly in the context of instance segmentation,
Mhm.
and how does this possibly affect the performance of a model?
So the hedging is basically like when we started, like I said, you try to predict or you try to like find objects everywhere in the scene, right? And hedging basically comes from how you treat the NMS or how do you sort of account for the NMS. So if you explicitly remove duplicates, maybe you will not have so much hedging. But if you do not suppress these extra, like based on how you suppress or delete the extra predictions, you will have different amounts of hedging. So modern segmentation methods will not remove extra false positives at all. They will just decay the confidence but keep them, and that is what we call hedging, because your network, you are trying to like hedge, you're trying to bet that there is some object here, some object here, some object here, right? But you're not sure, so you just keep a low confidence. So if by chance you actually match up with some ground truth, you get extra points.
Okay.
You get extra MAP points for that. That's basically it.
And you touched on it there a little bit, but maybe just to make it explicitly, like low confidence predictions. What does this mean, and like what's the problem with this?
Oh, okay. So a low confidence prediction is just, so the network outputs, your detection networks will, or segmentation networks will output like a binary mask with a confidence score as to how confident it thinks there is an object here, right? So the thing is, if there were like, instead of 2 cups here, let's say there were like 20, right? Then if the model is not sure, right? Is there like, if there is an occlusion, is it the part of the same cup? Is it a different cup? Like occlusion creates a lot of these problems, and clutter creates a lot of these problems where you're not sure if this object is a part of something else, right? So to be sure, you predict this object and you also predict it separately, like you predict all combinations.
Okay.
Kind of thing. It's a, like we discuss this more in detail in the paper.
Yeah.
But this is basically the network trying to predict as much as possible, so that if one of them actually lines up with the ground truth, you get MAP for that. But if it doesn't line up, the MAP is not, the MAP does not penalize that problem. So you are incentivized to predict as much as possible to improve MAP.
And speaking of hedging, you talk about 2 types of hedging in the paper. There's spatial hedging,
right,
and category hedging.
Right.
Can you describe these a little bit more in detail for us?
Sure. So spatial hedging is what I've been describing so far, where you try to predict as much as possible, around the area, and if one of them lines up with your ground truth, well and good, you get some MAP for that. Right. Categorical hedging is basically when you make a prediction, like if I ask you what is this, right, you would give me like some outline, and you would give me one object that you think it is, right? So maybe if I show you a Cybertruck, I ask you what is it? Is it a car or a truck, right? You will give me one answer. You'll not tell me it's a car and a truck, or like something like that. So or let's say a furry animal which looks like a dog or a cat, but so you might not be sure, but you will give your best guess, kind of. You will not say it's a dog or a cat or a sheep or a bear. You will not assign it 4 labels. But categorical hedging is essentially that, like you assign multiple labels to the same prediction, so that if one of them lines up with the ground truth, you get MAP for that. But if none of them line up, it's okay. You don't get penalized.
What's kind of like the fundamental difference between like categorical hedging and like multi-label classification or something like that?
That's a good question. So when you say multi-label classification, do you mean like in the scene, like a just like a multi-sigmoid classification? Like given a scene, just tell me what objects are there without counting them? Or...
Well, I guess kind of like you were mentioning, if you see a furry animal, right? That furry animal could be a mammal. It could also be a dog. It could also be a puppy.
Right.
And it also be a,
Yeah, I think that comes to like some kind of fine-grained classification where you want to like have. Yeah, I think in those cases, evaluation again becomes tricky. And I mean, this is a more broad observation, is that depending on the task, your evaluation gets trickier and trickier. So with segmentation, with multi-label classification, there is probably no one way of doing or evaluating things. And this actually gets hairier with all the generative AI you see. So for example, if you generate some image, right, how do we evaluate this image is good, right? It's very like people use all sorts of proxies like FID and all that. Like people use proxies to determine how realistic this is.
Yeah.
But that comes from the bias of another model. So if the model has never seen a Cybertruck, it might just say this is metal. It's not a car. Might say it's not. It's an unrealistic image, while it might be realistic. So it's all about like the evaluation gets trickier and trickier once the task has more facets to it. Classification is probably the easiest one. Even in classification, sometimes accuracy is not the best way to do things. Like if you have skewed classification, you would want to use the F1 score and not accuracy, for example.
Just curious, like would instance segmentation or segmentation in general, like would it work differently for like generative use, like let's just say generated synthetic images than it would for actual images?
It may, depending on what's the domain gap between the synthetic and real images. So if the synthetic images are really cartoony or out of distribution, then there is no guarantees on how the segmentation might work. There's like a huge community trying to do this sim to real domain gap problem. Yeah.
So let's jump into some more questions about the actual research paper.
Sure.
So again, like you mentioned that you discussed the limitations of average precision for evaluating instance segmentations.
Right.
Can you kind of give us a little bit more detail about what these limitations are?
So I think the primary limitation is that MAP is good at pretty much only one thing, which is to detect sort of, like MAP will basically reward you for every true positive that you find. And that is what MAP is good at. So if your MAP is low, you know that you are not able to find enough true positives. So you're not able to detect enough in the image. That's what MAP will tell you. Apart from that, how much of the extra clutter you're predicting is something that MAP will not tell you about. And this is like we were working on this part counting application and like neurosurgery applications where counting is very crucial. So if you have one object, or let's say if I ask you how many T packets are there in this clutter, you need to count very accurately. You might not want to, you might not care about the actual delineation or the actual boundary so much, but you just want to count this correctly, right? And segmentation can do that, but if your segmentation has this hedging problem, you would overcount the number of sugar packets, for example.
So you propose two new measures to quantify the amount of spatial and categorical duplicate predictions. Sorry. If we can really just quickly give us a intuition behind spatial categorical duplicate predictions, like what does this mean?
So the duplicate prediction is essentially the false positives that I described. So if you have, for the same instance, if you are predicting multiple predictions, like the predictions basically overlap with each other, that's sort of the spatial hedging problem. And categorical hedging is basically you try to guess the class of the object. And that is exactly what we try to measure in these two metrics that we propose. Yes.
And how do these improve the average precision metric?
They do not actually. So these are basically, think of these as like complementary metrics that you would use. So MAP will tell you how many how good so MAP will tell you how good you are at finding true positives. Our metrics will tell you how good is your metric at not hedging, or how bad your metric hedges. So these are like complementary information that you get from different metrics, and they're not supposed to like reinforce each other or something like that. But if you have these three metrics and more metrics, you get a more holistic idea of what your instance segmentation network is doing.
And you introduce also, as we mentioned earlier, semantic sorting and an NMS module.
Right.
How does this work, and how might it help mitigate some of the issues that are associated with duplicate predictions?
Right. So our motivation was mainly that if you have a pre-trained model, right, which you want to use, which is very good at MAP, which means it has excellent true positive finding capabilities, right? So it can find a lot of the objects in the scene. That's why it has a high MAP. You have this network, right? But you see this network also has a lot of hedging, right? So you want the network modulo the hedging part, right? So to mitigate the hedging, we propose this semantic sorting and semantic NMS. And the idea is basically to use a semantic segmentation to filter out the duplicates. Um, the details are a little more involved. I would encourage a reader to look at our paper for that. But the basic idea is that like a pixel in an image can belong to at most one object, right? That's the sort of basic idea. And then semantic segmentation is exactly that. Like each pixel is assigned a semantic label, right? And so your instances have to go through this semantic segmentation, and that's how you determine if multiple objects are trying to claim the same set of pixels. That's how you remove the hedging.
And how do you use the hedged predictions concept to kind of critique current network designs for instance segmentation?
I wouldn't necessarily critique. Like a lot of the top-down methods, a lot of the methods that we evaluate are actually like the motivation is very clear. Is that we do not know how many objects are in the scene, so we try to, assign at each pixel, or not each pixel, but like each grid location, like some object, and if there isn't any object in that location, it's okay. We'll not predict anything. So this is basically like the motivation is pretty good, but like there are like these side effects, and this happens because MAP doesn't penalize this aspect, right, of hedging. So if MAP penalized hedging, then we would have designs that are built to, like, because we build designs to improve MAP and not to find these side problems. So if a metric told you everything, then network designs would have been built to consider everything, and we just show that most methods try to benchmark on MAP, and that's why the blind spot has gone unnoticed for a while. I think it has been noticed, but hasn't been addressed. Because I spoke to a lot of people in the poster, and especially a lot of senior folks came up to me and they like, I can quote one of them, like, MAP sucks. And that is because they have like seen these problems firsthand, but it's like hard to address or hard to see what's exactly going wrong. And that is what we have tried to cover in this paper. There are other papers that have done this in different, with a different perspective. We have approached this from the hedging perspective.
So you also discussed this concept in the paper, visual crowding. So the concept of visual crowding in human vision,
right?
And then you drew parallels to instance merging,
right,
in instance segmentation,
right?
Can you kind of explain this analogy for us?
Okay, so visual crowding is basically there's a lot of noise.
Yeah.
So visual crowding is basically the idea that if you have, as a human, if I see this curve in isolation, I can predict this very easily. Like if this is the only object I see, I can predict its boundary and its class with remarkable accuracy. Whereas if you keep like a bunch of the same object, that is what visual clutter is. Like now you have to be very, like, you have to look very carefully, try to see if occlusions make it look like, so if, for example, right, maybe it's not very clear, but like the cup is sort of occluded by the kettle here, and I actually see two cups here, right? So I have to make this inference that this is actually one object and not two objects, right? And you can complicate this further by adding more and more objects in the scene which are in close proximity to each other, right? That is basically what visual crowding is. And that is what top-down instance segmentation methods do, where they try to predict something at each location. So if there are many objects, you will try to merge these instances into each other, kind of. And we show some qualitative examples in the paper where birds that are placed very close to each other are like clustered into one thing. Zebras that are moving next to each other are like clustered into one zebra, stuff like that. And this happens because of proximity, mostly, plus crowding. So yeah.
So you propose a plug and play module to
right,
mitigate issues with duplicate predictions.
Right.
So we talked about duplicate predictions and why they're problematic already. But what does this suggest about the potential for modular design and deep learning?
I mean, deep learning has been very, like, the design the design has been very modular from the beginning. So you started off with, like, when like TensorFlow, PyTorch, Caffe, these packages came out, they were very modular from the beginning. Like you have autodiff each component, like each layer wise, and then you just stack up the layers, right? That has been very modular. We wanted to keep the design modular because there has been a lot of work done on training these networks, right? And so we would not want to like start from scratch again. Like we show some problem, but do you want to really start from scratch training all these models? No, you want to like have something that just clears up the clutter, So I think modular designs are key because people can now the community can build on each other's projects, So I think, yeah.
So your paper also discusses the limitations of current metrics for evaluating instant segmentation models.
Right.
So what's this tell us about the challenges of measuring performance in deep learning more broadly?
I think, like I said before earlier, it's like different tasks will have different aspects. So something like single class classification might be more straightforward to evaluate. You just have like some kind of accuracy or F1 score. Once your task has more and more, like sort of complexity, your evaluation also has to keep up with that, or has to, like, a single number is basically one dimensional, right? So you are capturing only one aspect of something. And so if you need to capture multiple aspects like counting, sort of hedging is basically hedging covers multiple things. You want to capture precision, which is what MAP is kind of, right? So you need to, like, as your task becomes more and more complex, you need to evaluate it more critically. And with, let's say, again, with generative AI, it's even tougher because there is no way to evaluate. Like, humans can always evaluate, but how many humans can you have sitting and just clicking on, is this a good or bad evaluation? Even then, there are like things like, for example, uh, why is this image bad? Or maybe it looks realistic mostly, but there are like 7 fingers on the hand, right? That is a very common problem with stable diffusion. Maybe that's mitigated now, but like you have more and more sort of like dimensions to the evaluation. So yeah, I think we need to critically think about how we evaluate these things.
So as we picked up through the conversation, the paper kind of it critiques the focus on achieving high map scores in network design.
Right.
Did you ever once just think about naming the paper MAP sucks?
I think it's not something that like the community would like. I think I also don't think MAP sucks. I think MAP has good strengths, and I think at the time MAP was designed with the challenges in mind back then. And I think back then the challenges were how to segment objects precisely, or how to make sure that predict everything to trying to predict only the useful things. So now, yeah, with a shift in design, I think there should be a shift in evaluation criteria also.
So, kind of more serious question there is, so what's this critique kind of reveal about the relationship between the goals of researchers and the practical needs of a end user?
Right. I think researchers generally try to find interesting problems, and like it may or may not have any product incentives, as to speak. Some of it is motivated by trying to like sort of top leaderboards, and you need some way to measure progress also, right? I think folks in the industry are rightfully so more motivated by revenue and products that sort of help them achieve those revenue goals, right? So a lot of people that reached out to me were actually industry folks, and they were like, we do segmentation for so and so application. We notice that MAP doesn't tell us anything useful about our work, right? And at some point, some folks have stopped using MAP and just qualitatively evaluate their methods now. So there are some sort of, I guess, incentive misalignment, or like some kind of misalignment between researchers and industry, but both of them are always like try to make progress in their own ways.
Yeah.
So I think. Yeah.
So I'm just curious, like qualitatively evaluating their models is just like literally just looking, and that's
that's pretty much it. Like they know so industry folks know what the hard examples are in their application, right? So they keep those hard examples for later, and then they just like, okay, this method is not getting confused, or this method is giving me good mask quality or so and so. Like the MAP basically tells you the same number pretty much for all these images. So you're like, I don't know what. So, yeah.
So we talked about how you drew inspiration from human vision to address this instance merging idea.
Right.
What are your thoughts on looking to biological systems for solutions to challenges in artificial intelligence?
I guess we all do that in some way. Try to look at human, like biology maybe, but like so a lot of the studies around like neurodegenerative diseases, or like balance syndrome, for example, where you lose like some kind of object permanence. So people with balance syndrome can only look at one object at a time. So when you look at this object, you still have other objects in your periphery, but some people will not see anything apart from this one object. And once they shift their gaze, they now see the new object, but they forget that the old object, they can't see the old object now. So these different diseases tell us how the human brain functions in some ways. And then we can use some of these as inspiration to design AI, or, like more sophisticated models that maybe do not have these deficiencies, or, I think biology is just a great marker for, like, our brains are basically a good reference point, I guess.
Yeah. So kind of just digging a little bit more deep into that, like, as we develop these more sophisticated methods for instance segmentation and other visual tasks, what are some potential applications or maybe sectors that these advancements could transform?
You mean like segmentation?
Just these more advanced kind of methodologies as more sophisticated methods are coming out.
I think the major sort of progress with like transformers or even generative AI, I think, is like we are trying to sort of mitigate this data gap with synthetic examples. For example, like we are trying to generate as many images as possible, try to take the mturkers out of the loop, because annotation efforts are very costly. So, and I'm not very sure about like transformer architectures. There was like some back and forth between CNNs versus transformers. I think Connext sort of showed that CNNs are still good enough. I think it's all about like what is the representation capacity of these models, and what these models actually learn, that maybe differs from architecture to architecture, or so on. I think I don't have a like very concrete answers to this, but I think we'll just find out, I guess.
Yeah. Let's wait and see.
Yeah.
So what challenges do you think are under-addressed in deep learning, and how do you see the field evolving to tackle those challenges?
I think at least in my paper, I try to point out that evaluation is still something that we do not think about a lot. We just go with whatever benchmark we are handed over, and try to optimize that benchmark. The other problem I see is maybe, which is again one of the quote unquote boring stuff, is what do these networks learn actually, like interpretability of these models. Like, if you ask me to give my worldview or whatever, like you may not have access to all the neurons in my brain, but you will have an access to the mental model via asking me questions, asking me to draw stuff. Like you can ask me about my life experiences, whatever. You have a pretty good mental model of me, and people do use that to infer about behavior of other people, right? If I talk to you like for 2 days, I know what kind of a person you are, what kind of things you like, so on, and how should I interact with you, and so on, right? Deep learning, we cannot do that with deep learning. We only have an access to deep learning via the predictions they make. I think we do not have any kind of idea of the mental model of deep learning methods yet. I mean, there is work, obviously, but I think we are not as mature as we are, let's say, with segmentation.
Do you know like any papers or anything that touch on this?
Off the top of my head, I don't recall a lot of things. There is the MTOM paper, Machine Theory of Mind paper, which tries to build a mental model of AI agents, not just AI agents, but they have like random agent, they have an RL agent, and so on. That's a good starting point, I think. And then I think there were like some papers on the Minecraft challenge, So where they were trying to make inferences about the like a Minecraft agent who's trying to explore its world and trying to build tools like but diamond pickaxe and all that. So you need like a hierarchy of things to progress to that point. So I think theory of mind is a good starting point for these kind of things. I'm not sure if there are like other works. At least I'd have to look up my reference list to find out. But yeah.
So like to ask this question to everyone that comes on the show. Can you describe a moment or a project where you grappled with the limitations of deep learning? And limitations can be however you want to define that term. And then how did you navigate those constraints and those limitations?
I think I'm a relatively like very junior researcher. I mean, yeah, junior researcher in the field. Most of the problems I have tackled are basically have converted into my sort of papers essentially. So this paper was basically born out of like I did not start off with saying, oh, MAP is bad. I started off with trying to apply some segmentation on some application. I saw that okay, this is looks pretty bad. And for the longest time, I thought this was maybe a bug or something, And I found out after like some digging, I was like, oh, this is a problem with the metric. And so I think some of the problems I've also encountered around the interpretability aspect is that I've been working on like some optimization algorithms, and with optimization, you know what's going on. You can plot every step of the way. With deep learning, it's more abstract. You have to like trust the network in some sense.
Can you share like that what project or problem that was that you're working on where you kind of came to this realization?
When I came, the MAP project was one of them where I came across a problem.
Like, was it like what type of data set were you working with? What type of
this was the neurosurgery data set. So we had the neurosurgery and we had a part counting data set where basically like there was like a bunch of objects in the scene and the task was to just count how many there are. So this was like, think of this application as something like you are in a manufacturing factory or whatever. There are like, products moving along some kind of conveyor belt. You want to just count, take inventory or something, right? And that is where we saw like nothing was working and we were like, but our training is good. Like, our MAP is like pretty good. Why are we not able to count? Why are we counting thrice as many objects there are,
Yeah.
And then we looked at it deeper and we're like, okay, this is not good,
Yeah.
So
Oh, go for it.
No, I was just saying that, problems like you just encounter problems when you work on some project and you are like, oh, this is like mostly I think the problems are orthogonal or somewhat orthogonal to the problem you work on, and you can choose to sort of push that problem under the rug, say that, oh, this is not like my thing, or you try to like build around it.
So what did this experience teach you about balancing theoretical advances and practical implementation?
I see. I think there should be, as a researcher, there should be a balance between like theoretical understanding of what you are doing versus practical applications. Without practical applications, there's no point in doing all of this, I think. Right? If something is like, if there is something that no one uses, I mean, there's also like a bit about sort of future promises, like something might not work now, but maybe 20 years down the line, you might have the tech to make it work. There's always ambiguity around this. I try to keep a balance between theoretical understanding of deep networks and like which sort of leads to statements about practical applications. So if you read the paper about MAP, if you are a practitioner, you will hopefully make more informed choices about how to evaluate your segmentation.
Rohit, thank you so much for taking time and joining and for being patient with me as I was trying to figure out stuff.
Very fun talking to you.
Where can people find you if they want to connect with you online?
I am on multiple social media. I'm on Twitter. I'm on LinkedIn. I have a personal website with like I try to write a blog, not very regular, but I think these are the main. I'm also on Facebook, which I don't use anymore, I guess. But Twitter and LinkedIn are the places where I'm most active.
Okay.
And yeah, I also have a website if you want to check it out. Yep.
I'll be sure to link to all that stuff. Rohit, thank you so much, man.
Thanks so
it's
much,
great chatting with you. Take care, everybody. I'll be back. We got a full day of interviews lined up. I got like 2 more happening, so stay tuned. You'll see me. Hopefully the background noise wasn't too distracting. I'm gonna try to move locations and get this a bit nicer. Take care, everybody. Bye.